Okay, after class last Thursday, I got a request on one of your feedback cards that I go through the Excel file a little more slowly. And so what I'm going to do is I'm going to take the example that we were doing in class, and I'm just going to start with a blank Excel file with nothing in it except the data. And I'm going to go through and I'm going to show you what I'm doing. So here we have a column for the control raw data, a column for the data where they shone light on the back of the knees, and a column for where they shone light in the eyes. And once again, they're looking at a shift in the circadian rhythm. And the shift in circadian rhythm is positive if it's a shift forward and negative if it's a shift back, if I recall correctly. So what I'm going to do here at the beginning is I'm just going to start setting up some rows where I can store information and I know what information is going to be in those rows. So I'm going to put in row 11 sums of things. I'm going to put in row 12 counts of things, and I'm going to put in row 13 averages. And so for control here, what I want to do if I'm going to calculate the average is I'm going to add up all of the values, and so this would be equals sum, and then I'm going to just highlight the things that get added up. And if I recall correctly, I think I may have messed this up. Oh yeah, I missed one of the values because I was copying this over from another sheet. So there is actually a value here, and so I have to redo this sum and go all the way down to B10, not B9. So anyway, that's the sum for all of those values. And then I can count however many values there are by using the count function, and once again highlighting the data. And if you want to, it's oftentimes useful to actually make yourself a column for replicate number. 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 there. And I generally like to take everything, and I like everything to be centered because I'm just kind of that way about things. And then one way to calculate the average would be to essentially take the sum and divide it by the count. And so the sum is in B11 in this case, and we would divide that by the count, which is in B12. And I'm actually going to do another thing here. I'm going to run this over and put a double border on the bottom of that to separate data from calculations. So this average should be the mean, and so we can actually maybe rename that mean. And then I also can verify whether I am calculating the average correctly by just using the average function. So type in average, once again highlight the range of data that you want to be averaged, and hopefully those two numbers turn out to be the same. Now, once I've done this for one column, I can actually just copy that and paste it there and paste it there. And then when you highlight that and you go and look at that, you can see that that's the sum of those items. You can see that this is the count of, once again, those items. You can see that this is that sum divided by that count. And you can see that that is an average of those values. And the same thing is going to be true over here as well. So the thing that I like about doing this in Excel is once you've done something once, it's easy to do it again. So as we embark on doing an analysis of variance, we need to next calculate the sums of squares within a sample. And so I'm just going to make another column, and you see that I have left myself space next to each of the columns of data to do these calculations. So I'm going to use that space to put in columns for sums of squares within. And recall that the sums of squares within is simply equal to, and then you would open the parentheses, and it's simply equal to the value from the data set minus the mean, and then you square that. But since you're going to want to do this for every item in this column, it's good to use what I call a static cell reference, which is to put a $sign in front of the letter and a $sign in front of the number, the letter being the column and the number being the row, so that when you then go and run that equation is up here, and you can see that it's referencing the mean down here. And it should reference that mean so that when you copy this and paste it, that is still referencing the same cell of the mean. Once you've done that, all you have to do is copy that all the way down, and you'll see that it continues to copy that same formula. It's shifting the cell that is the data point, but it's keeping the mean cell the same. Well, now you can copy this formula. You can come over here and paste it in, and because that first value is actually not static, it's actually going to just go and look at the cell before it. So it's looking for the first of the knees, that's E3. Now you can just change that B in the static cell reference to an E. And now you can see that this is referencing the mean for knees. Once you've done that once, you can once again copy that down. If you want to, you can go and check and make sure that it's still referencing the correct values in calculating this. And then you can copy that formula over again, and you can paste it in. And now this is going to be referencing column H, not column E. And so you just change what was the E and you change that to an H. And now you're referencing the mean from the I's column. And then you can just copy that down. Now, here at the end, we are going to want to sum that. So you can actually just copy this formula over. And when you look at that, you can see that it's summing the sum squares within. And you can do that for that value. You can do it for that value. And you can do it for that value. And once again, when you go and check those things, you will see that each of those is actually just summing the column above it. Now, the degrees of freedom for sum squares within is different. It's 1 minus the sample size, and so you can actually, once again, get this to calculate it automatically. You just take the count for that column and you subtract 1. And once again, you can copy that formula and paste it there and paste it there. And so now you have the sums of squares within each of your treatment levels. And so you can just come down here and make yourself another row title where you're going to get the sums of squares for the entire experiment by essentially adding these three values together. So type in sum, and then you want to use the Alt or Command button on your keyboard and click on the first value, the second value, and the third value. Close your parentheses, and that should give you the sum of all of those things. Then you can get the degrees of freedom within, which is simply the degrees of freedom of each of those, which once again is going to be the sum of, in this case, the 7, the 6, and the 6. Close those parentheses, and that should give you 19 degrees of freedom. So you've now calculated the sum squares within. So the next thing that you need to do is you need to calculate the sum squares among treatments. But in order to do that, you need to know what the grand mean is. So we need to make ourselves a header here for the grand mean. Make a row for the grand mean. And all you want to do here is type in equals average, and then open our parentheses, and once again, highlight all of the data from the control, all of the data from the knees, and all of the data from the eyes. And once you've done that, that should give you the grand mean. Now that you've done the grand mean, you can make yourself a row for sums of squares among. And when you do sums of squares among, this is once again equal to the difference between the sample mean and the grand mean, but it has to be weighted by the sample size. So the way I'm going to do it is I'm going to always put the sample size first, and then I'm going to multiply that times the sample mean minus the grand mean, and then that gets squared because once again this is a form of variance. And because I want this to be a static cell reference for the grand mean, I'm going to put a $sign in front of the B and a $sign in front of the 19. And since all of these means are going to be compared to the grand mean, I don't have to change that as I move from control to knees to eyes. So once I have that calculated for the control, I can just move over, paste that same formula underneath knees, and it will calculate it automatically, and paste that same formula underneath eyes, and it will calculate it automatically. And when we click on that cell underneath knees, and we put our cursor up here in the formula bar, once again, we see that it's taking 7, which is blue, times the red value minus the static cell reference of the grand mean squared. And so we can verify for ourselves that we are indeed calculating that correctly. And so then what you want to do is you just want to come out here to the edge and say, okay, we need to sum all of that up across all 3 treatments. And so we can sum everything that is in this row. And when we sum that up, it should be that. And in this case, the degrees of freedom is simply 1 minus the number of treatments we have. We have control, we have knees, we have eyes. So the degrees of freedom in here will be 3 minus 1, which is 2. Now at this point, we have everything that we need to make an ANOVA table. So I like to put my headings in first. So we have a source of the variation. We have the sums of squares. We have the degrees of freedom. And then we have the mean square. And then we have the F. And then we have the P. The P value. And once again, because these are headings, I'm going to want to go ahead and put some separation here. So I'm going to once again use the double bar. And the sources that we have is we have variation that is among our treatments, we have variation that is within our treatments, and then we have total variation. And so once again, we can make some separations so that we keep our rows separated from one another. So once you have this all laid out, you can just go and get the total for the sum squares among, which is just type in equals and then go and highlight the cell where that occurs. Same thing for sums of squares within, go get that total and type it in there. Degrees of freedom is for among, is right there. And let's go ahead and label that up here so that we don't forget which degrees of freedom that is for. And the degrees of freedom within is up here. Now, we can take the total by essentially summing the things above that. So the total sums of squares should be the among sample sums of squares plus the within sample sums of squares. And in a similar fashion, the degrees of freedom should also add up. And this is one of those times when you want to check sample sizes and things like this in degrees of freedom. So we have 8 and 7 is 15 and 7 is 22 total sample size. The total degrees of freedom should always be 1 minus the total sample size. And so that's your first check to make sure that you've done your degrees of freedom correctly, is this should add to 21 rather than 22. The other check that you might want to do is to look at the total sums of squares and see if it matches what we would expect. Because in this case, we just added these two numbers together. But you can always go back and figure out the total sums of squares using the concept of total sums of squares, which is how much does the data as a whole vary from the grand mean. And so we can basically come over here and we can take these headings once again, and let's just copy them into another set of columns. We're going to get rid of the sums of squares within because we don't need sums of squares within. And I'm leaving this spacing the same because that's important when we start referencing things. So in this column here, I'm going to want to take, so put an equal sign in there, open your parentheses. I want to take the first value of control, subtract from that the grand mean, and I want to square that. Now, once again, all of these values are going to use the grand mean, and so we can actually put in a static cell reference here, so it's always referencing the grand mean, and that's what we have. The difference between this value and the grand mean is 1.54. Now that we have that, we can copy that all for the control. And because we have a non-static cell reference and a static cell reference, when we copy that and paste it over here for knees and highlight the formula up here, it should be taking the first value of knees, then it should be comparing that to the grand mean and squaring it. And so that means that that's doing that appropriately for knees. And so we can then just copy that down for the 7 values in knees, and then we can do the same thing for eyes, and it should be fine. Now, I like to use color coding to separate things. So I'm going to put this in yellow so that I know that this is something different, and I am going to give it a title up here, which is basically sum squares within check. So this is just me checking to make sure that the sums of squares within is correct. I'm going to merge that and center it. I'm going to put a double bar beneath that, once again, just to keep things straight. And then this whole thing should add up to the sums of squares total down here in our ANOVA table. So let's go and see if that actually works. So we're just going to put sum squares total down here, and then we're going to sum up this entire block of data. And hopefully that 16.6398 is the same as 16.6398. So it looks like we did our calculations for sum squares within up here correctly, and we did our sum squares among correctly because this sum squares total, which is adding those two things together, equals this sum squares total, which is taken from conceptually thinking about what sum squares total quantifies. Now, once we have those checks done, we can now calculate the mean squared, which is simply the sums of squares divided by the degrees of freedom. And if you do that once, you can do that again for the mean squared within equals that divided by the degrees of freedom. And then F is simply the mean squared among divided by the mean squared within. And that gives us 7.28. And then we can go to Daniel Silver's website and we will find that the p-value for this test is 0.004, if I'm recalling correctly. So we've calculated the ANOVA by basically plugging in formulas in Excel that give us all the information that we need. So the next thing that we have to do in doing this is we need to basically conduct a Levene's test. So I'm going to go down here to row 30 and I'm going to put in all caps a Levene's test label so that we can know that we're doing something different down here. And what I'm going to do is I'm going to basically just come up here And I'm going to copy this whole block of material from up here. And you'll see why I'm doing this in a minute. And I'm just going to copy this whole thing. So just do Control C, and then down here do Control V, and it's copied everything. Now, know that there are some static cell references in here that we're going to want to change. And a Levene's test, remember, is a test on the absolute values of the deviations from the mean, and you're not squaring them or anything. So we're going to clear out all of the formulas for sum squares within. So just go and delete all of those. Then we're also going to get rid of all of the original data, because we're going to get data from someplace else. And so what we're going to do is, in this first replicate for the control, the value for this is the absolute value of the difference between the original data and the sample mean for that. And it's not squared or anything. It's just the absolute value of the deviation. But once again, we want to do this for all of the control data. So let's go ahead and make that B13 a static cell reference. And now when we do this, we will copy that whole thing down. And when we look at this last value down here, it should once again be looking at the 8th value minus the mean. And it's taking the absolute value of it. Now we can do a similar thing for knees. Control C, Control V, type that in. But once again, this is referencing B13, and we want it to be referencing E13. So just go in, highlight that B, change that to an E, and it's going to calculate the absolute value. And once again, we want to do this for the 7 values that are in knees. We can check the last one by looking at the formula. And when we look up here, it's once again taking the value minus the mean and giving us the absolute value of that. So we can then copy that formula, plug it into I's, and once again, instead of column E here, we're going to be wanting to do this in column H. When we highlight that and go up and look what's being compared, we're comparing the first value to the mean of I's. And then we can once again copy that whole thing down. Now, because we copied this whole thing from up above, we should see that this is now just summing the deviations. We have 8 deviations, and this is now the mean of the deviations, and we can check that this is the average of the deviations. So now it's calculated all those things, and we didn't have to write new formulas because those cells have flexible cell references, and when you copy down, it transfers the cell references relative to the cell that you're in rather than it being a fixed cell. But because the fixed cell because up here the fixed cell was the mean up here, we don't want it to be the fixed cell of the mean up there. So we can come back down here and we can just calculate the sum of squares within of the deviations from the mean deviation. So this is simply going to be equal. We did this up above earlier. The actual value minus the mean. And in this case, we're doing an ANOVA on this. So we're going to square that. And once again, we're going to make this a static cell reference because we want it to always be referencing that cell. And now we can copy that whole thing down. We can take this last one and give it the lower border again. We can check this again and we can see that it's referencing the mean. So now that we know that, we can copy this formula, paste it in here, and once again, it's doing all the right things except that it's referencing the mean for the control, and we want it to reference the mean for the knees, and so we want to change that B to an E. now it's going to be referencing the correct mean. And so we can actually just highlight that cell, drag it down, copy that formula over, paste it there. And once again, we want to take that E and make it an H so that it is referencing the correct mean. And then we want to drag that down. And once again, the sum at the bottom here should be summing the values above that. And because these cells are in the same place relative to the sums of squares within, this sums of squares within should actually be summing up those three columns. Our degrees of freedom are the same. Now the grand mean is once again just a sum of all of those values. And so when you put in the deviations, it had automatically calculated the grand mean for you. So now the only thing that you have to do is in the sums of squares among, you need to change the reference for the grand mean, because you can see that it's not referencing this grand mean, it's actually referencing that grand mean up there. So that's a pretty simple fix. You just take this B19 and you put in the row number that the grand mean is, which is B49. And now you can see that you're referencing the grand mean. That changes that value. You can paste it into there, paste it into there, because you have this thing auto-summing the things that came before it. You've now calculated the sums of squares among. And because this ANOVA table is referencing things that are up here, you can see that the ANOVA table has been populated with the values that you've been going through and calculating. And so you have the sums of squares among matches the sums of squares among, sums of squares within matches sums of squares within. The degrees of freedom are the same. The mean squared is once again simply the sums of squares divided by the degrees of freedom. It recalculates the F, and in this case the only thing that's not correct is the p-value, and then you can just take this F statistic with this degrees of freedom and this degrees of freedom in the numerator and the denominator, and you can look up the p-value, but you can already see that that's a really low F value, and so you should expect the p-value to be relatively high, and I think we found that it was like 0.85 or something like that. We can just actually go to Dan Soper's website if you want and look that up. Daniel Soper, p-value calculator for an F test is f.183, 0.183. We have 2 degrees of freedom in the numerator, and we have 19 degrees of freedom in the denominator, and the p-value for that is 0.8342. So my memory was a little off, 0.8342. Once again, that's much higher than 0.05, and so what we've done is we've calculated a Levine's test where we're basically looking for differences among the deviations in the 3 treatments, and what we find is that there are no deviations. There are no differences in the deviations among the treatments, although we did find that there are differences among the means. What we're going to do in class on Tuesday is we're going to be looking at these deviations among the means, the differences among the means, and we're going to run a 2-keys test on these data to test whether or not, well, to test for which means are different from which other means. So hopefully that takes you through how you go about calculating this in a little clearer way in an Excel file. I'll also make a screencast of how to run 2-keys test in an Excel file like this as well. And I'm just going to append it to the end of this because we'll be using figures that we've already calculated up here. And then in that way, you'll be able to do everything in Excel. And on your problem set, I would recommend that you do this in Excel. One of your problems is fairly large. I think it has 84 values total in it across 4 treatments. And it's going to be much easier for you to do this in Excel than it is to do it out on paper. I'm fine if you do it on paper, but you're probably going to have a better time doing it if you just try and do it in Excel. So I hope you find this video useful, and I will see you in class.